Hey guys, welcome to our lesson entitled Modeling with Linear Functions. Okay, many real-world situations can be modeled by a linear function because they involve a constant rate of change. Now, that constant rate of change that we are talking about there, that's what we use the word slope for. So I'm just highlighting that. And remember, whoopsies, that is slope. And it's a rate because remember, it's something over something. So when we have real world situations, we'll have some actual units to put in there. Okay, so for instance, every time you take a trip in a car at a constant speed, the distance traveled is a linear function of the time. So I know you guys remember this formula, D equals RT, which we call the DIRT formula. It's distance equals rate times time. Well, in this case, the rate, that is like your slope. So we're going to do an example like this down below so we can easily understand a linear situation. We have a few learning targets that we're going to be addressing during this entire lesson. One is that we can write a linear model for a real life situation, given a description in words, a graph, or a data table. The other one is that we can interpret a linear model. So that means we can be given a model and tell what it represents. And the last one is we can utilize a linear model to solve real-world problems. That means we're given an equation and we can use it to answer questions about the situation. All right, so example 1, you are traveling in a car at a constant speed of 7 miles per hour. The linear function d of t equals 70t models the distance d traveled after time t in hours. So what we have here, guys, is we are actually given the linear model. So the model means equation, okay? And this is in function form. So remember with function, the input is what goes into the parentheses. Okay, and the output is your, like in this case, it's the D. So it's what's on the outside of the parentheses. Okay, also your input is your X, which is usually, that's your independent variable, and your output is your Y, your dependent variable. And the general function form, remember we use f of x. So when we have these real world situations, it's nice to use letters that pertain to the situation so we remember what they represent instead of just f and x. So given this function, I'm just going to write it down here again. D of t equals 70t. Identify and interpret the slope, the y-intercept, and the independent and dependent variables. So I'm actually going to start with the independent and dependent variables because I just was talking about input and output. So independent variable, that is our input variable, which is usually represented by x in our general function form. But in this case, our input in the situation is t, which represents the time in hours. Our dependent variable then is the variable that depends on the input. So that time that we are driving determines the distance that we are actually driving. So this is our output. And so that is our D, which is the distance driven after time t, if you would like to add it. Okay, so our slope, remember, is that constant rate of change. And in the problem, it told us that we have a constant speed of 70 miles per hour. So whenever we ask you to interpret the slope, I want you to write it with those units. So the slope is 70, which means that's our speed, or our rate, if you will, of 70 miles per 1 hour. Or you could say we cover 70 miles in 1 hour. Okay, either way is fine. I just want you to understand that it is a rate and it has 2 units. The y-intercept, remember, is our b value. So if we just had f of x equals mx plus b, in our case, we just have 70t. So that'd be like 70x plus b would be 0. So our y-intercept is 0, and that's because that is our value that we start at for a distance. So basically, this is our distance traveled at time 0. Or after 0 hours. So basically, right, we start our trip, we haven't traveled at all. So that's why it's 0. Okay, using this function, we're going to do the rest of the problems. Letter B says, fill out the table of values according to the situation. So at time 0, remember, time is our input. This is what determines the distance traveled. We've obviously gone 0 miles. After 1 hour, we've gone 70 miles because we're going 70 miles per hour. After another hour, we'll add another 70. That's 140. And I'll keep going down the table. Then we'll have 210. Then we'll have 280. And then 350. And finally, 420. And I could keep going, but this is a good beginning of a table of values. This table of values, while it isn't a table, I want you to understand that what I've done here is I've actually made some ordered pairs that we could plot on the graph. So you don't have to write all of these. I just kind of want to show you. So at 2 hours, I'll be driving 140 miles after 2 hours, excuse me. So we can use that to help us do letter C, which says graph the function with the method of your choosing, label and scale the axes. So if our input, our independent variable, is our time, we're going to put that on our x-axis, but we're going to call it our t-axis. That's in hours, and let's just go by ones. Okay, our dependent variable goes on our y-axis. That's going to be our distance, and that's in miles. And looking at my table, I'm going up to 420, so maybe I'll just, every 2 tick marks, go 100 more miles. So 100, 200, 300, 400, and 500. Okay. Now, you could graph this by plotting the y-intercept and doing the slope, but it's kind of hard to plot 70 up 70 every time because the scale on our axes is going by 50s. So what I'm going to do is I'm just going to plot 2 points on the line and use a straight edge or my imaginary straight edge and connect them. So I'm going to plot 0, 0 because that's where this starts. And then I'm going to plot 5, 350. Okay. So I'm going to try my best to draw a straight line because we want to be able to use this to answer questions. And if you have a straight edge, please use it. Oops. Okay, not bad. Okay, letter D. Use the linear model to find the distance traveled after 3.25 hours. So remember the linear model, that's your function or your equation. And what it's giving us is hours. It's giving us the time. So my function was this, d of t equals 70 times t. So if I know the time, I'm going to plug 3.25 in for t. And so to find the distance traveled after 3.25 hours, I'm going to multiply 70 times 3.25. Now I'm doing this on a calculator, so you can easily just type this out, and what you're going to get is 227.5 miles. So guys, what that's telling us is after 3.25 hours, we will have traveled 227.5 miles. Letter E says your destination is 595 miles away. how much driving time will it take you to reach your destination? And we're not counting the stops here. So literally driving time at 70 miles per hour. So it's telling us a distance. So what we know is now we know d of t. Okay, so I'm going to plug that. It's going to take the place of this entire piece on the left. So 595 equals 70 times t. And then again, using my calculator, I'm going to type 595 divided by 70, and I get 8.5. And I'm going to label that because it's time, that's hours. So it'll take 8.5 hours to get to our destination if it's 595 miles away. Letter F, use your graph to check your answers for D and E. Okay, so D tells us that we are going to travel for 3.25 hours. So what we do is we go to 3.25 on the x-axis. And again, because oh gosh, my tablet isn't perfect and I don't have a straight edge, this is not be perfect. So there's about 3.25. And then I follow that up to my line. And then I go across to my distance. Now, using algebra, we found that was about 227.5, and I'd say that was pretty close with my line because this is 250, so about halfway through. So, looks like we did that one right. The thing about using a graph is it's always a little off when you're doing it by hand, but algebra is always perfect. So, letter E, we were given the distance we're going to travel. So the distance we were going to travel was 595. So that's like way up here, almost the top of the graph. Sorry about all the bells, guys. I usually try to do this at home. And that brings me there, and I come down. Now look at this. That looks like 8.7, but again, remember, I did this graph by hand, so it's not going to be perfect. It should have been 8.5, but it's close, right? So that's how you could also look at your graph and find those answers, or an approximate answer. Okay, I just wanted to make sure that we talked about these various ways to represent a linear situation. We are going to do the next two examples in class together and have some good time to practice. I hope you guys are having a great weekend. I'll see you Monday.